All right, welcome everyone. Okay, I know that kickoff is at 4:30 today, and I am going to try to get us out of here by 4:10 at the latest, so hopefully you can travel somewhere to go watch the game. I'm surprised to see this many of you in person. Shout out to those of you, maybe not a ton of American football fans, but get it. Okay, so this is a better example than Friday of what we will usually do for warm-ups. Can somebody give me a thumbs up? Is the poll everywhere live right now? Yeah, sweet. Okay. So this is hopefully a review from Friday. That's the goal. Remember, we were talking about how there's something called an ADT. That's functionality. Right now, we are asking you to implement a list. And this list is specifically going to be used to manage a playlist, like maybe on Spotify or Apple Music or whatever streaming format is your choice. Now the question is, we've learned some trade-offs. Maybe arrays have that contiguous memory thing going on. Maybe arrays make that sort of ability to jump into the middle of something really convenient versus linked lists. Maybe they're a little bit more convenient to move things around, more flexible. Think about the different types of actions you as a user would take on a playlist. How do you personally interact with a playlist? And then expand your empathy. How do others tend to interact with a playlist? And think about what is the most frequent interaction. Think about what you want to optimize for time or memory. And the fun part of this is there's technically no right answer. So I want you to take the next 3 minutes, introduce yourselves to new buddies around, because I know y'all are still looking for partners, and discuss and debate. Feel free to look at the poll everywhere. In like 3 minutes, we're going to talk about it as a group, and I want to hear what you discussed. Go. All right, if you haven't already answered something in the poll everywhere, make sure you go put something in the poll everywhere so that I can mark your sort of participation. Those of you watching this on Panopto, that poll everywhere will stay open until the next lecture. Okay, can I have a volunteer to maybe tell us which they picked and why? Array list or linked list? Anyone? Yes, please. Mm. Yes. Okay, so we have one vote, and the first thing that you thought about is the shuffle, and I think that's a great way to think about this. So I also didn't give you very much context on how to implement this, right? With intention, the goal is up to you. So in this context, how we would be implementing it sounds like each element is a song. In the array list implementation, we would have indices for each of, maybe those are song objects stored in an array of songs. So if you wanted to implement shuffle, maybe what you do is you just use a random number generator to generate a sequence of random integers, and then you just jump around to those different integers and you play those out. So I agree, in that particular context, array list, anytime you're trying to play not just from 0 forward, but in a different order, the array is always going to be faster to jump around indices. 1, because you don't have to start at the front and loop all the way until you find the different indices, but 2, because of that nice contiguous memory, we're sort of accessing pieces of memory all next to each other in your computer's RAM. Then we talked a little bit about how that might apply in terms of add and remove, but does somebody pick linked list and they want to tell us why that one's their favorite? Sure. Here. Yeah, you. Yes. Absolutely. And I think you'll find this is a common pattern if we picked linked list. Maybe you were thinking more about the add and remove because those tend to have a little bit more flexibility. So if we wanted to add something to the very beginning of the playlist, maybe you're like, this is the new song I want to hear the most. I'm going to put it at the top. Linked lists tend to be faster or easier to insert at the beginning because remember, with an array list, to insert something, it means we have to shift everything else to the right. And that's going to take a linear runtime to do all of that shifting because we have to touch every single thing in the playlist. So if you have a big playlist, that's a lot of shifting. Also, remember, arrays have a static size. So if you're inserting something and you've run out of array capacity, then we hit that expensive make a new array, copy everything over. These are sort of the basis of what I might compare and contrast array versus linked list here. Array, that tends to give us more quick access because of the indices. Linked list tends to give us more flexibility because it can grow and shrink in different ways. I'm going to look at the poll everywhere. Let's see. It should show me. There we go. 160 responses. Show me the responses, please. Okay, and I'm officially annoyed with poll everywhere. Never mind. They change their infrastructure every quarter. Why? Okay, I think I put some of these things. There we go. Maybe those are some whys. Both answers equally correct depending on how you justified them. Does anyone have any questions or other curiosities or things we maybe didn't consider that you want to bring up here as part of this discussion? Yeah, in the back. Oh, this isn't it. What if we can combine? And I think that's a great way to think at any point. If I'm ever trying to force you into a binary decision, always ask yourself, could I do something different? And so what we were just suggested here is, what if we had both an array list and a linked list? Could we do that? Now, immediate thoughts might be, well, would that be duplicating my data? Maybe that's expensive to store the same data in 2 places in 2 ways. Sure. But maybe we made a song object, and actually what we're storing isn't multiples of the song objects, but duplicates of references to that object. Still kind of expensive, but less expensive than storing the individual actual song data over multiple times. So depending on your scenario, maybe you do see that. In fact, when we get to really complicated objects like graphs, you'll see that we might store the same type of information in different formats across a multitude of different objects depending on the way we're going to interact with that data. So great thinking. Yes, we will get more complicated over time. Yes?
If we use that array list, is it also easy to reorder songs so we could just create like a temporary song object and store for one indice and then just change other indices to this temporary?
Yeah, so there are more clever ways to avoid the constant shifting. And I think our friend at the very beginning too was like, okay, maybe instead of we treat every individual ad as an individual item and we do all those shifts, maybe we sort of take in multiple, the new state, and then we create a temporary, we do multiple swaps in one. Yeah, those are things you could also do. But as you can tell, as we're starting to deviate from just array list or linked list, the other thing to keep in mind is how painful is that code to write and maintain, which is another thing that you are now going to have to consider whenever you're thinking about the design of your code. Because as it turns out, in school, we almost exclusively talk about runtime as a resource, but as a dev manager, I can tell you the most expensive thing I will ever include in my projections is dev time. The time it takes a human to read my code, interact with it, is going to be way more expensive than spending a few extra computer cycles. So at Google, for example, we cared a lot more about code readability, code maintenance, than we did necessarily like shaving off a few extra cycles, because humans are more expensive than computers. Okay, a delightful tease for you. We are going to continue these types of conversations throughout the quarter. In fact, this is going to be sort of the core skill that I want you to walk away from this class with. Yes, you will be able to code more complicated objects, but the thing that I hope you take away is, one, there's a million ways to implement absolutely everything, and those who can advocate for their position are most often the winners in any debate. And we will talk about that plenty, but as engineers, we tend to love anybody that's technically right, and I can't even begin to tell you how much of my career has been dictated by the fact that I just showed up with the data to the meeting. Come prepared, win the meeting. Are meetings really competitions? Yeah, it's like war out there. Y'all prepare yourselves, okay? Okay. Let's talk about some announcements. So first of all, I didn't say it at the very top, but I did post in the EdSTEM a Lecture 3 questions thread. So feel free to use that to ask questions. Shout out to the TAs for answering those wonderful questions from last time. I also put a link to these slides. I know they're not on the website yet, but if you want to follow along on this slide deck, there's a link to it on the Ed board. So we published P0 on Friday, and what that means is if you go to the course website, cs.washington.edu/373, there is now all of the descriptions for how to download IntelliJ and the JDK and the Git, and even some walkthroughs of the individual pieces of the assignment. If you couldn't tell, the questions in the assignment are literally like 143 questions I stole many years ago. I stole them intentionally based on what I think you might need to feel comfortable with in this course. So if you are still like, 143 or 123 was a while ago, or I didn't do them in Java, please give these things a try. I do this intentionally in the first 2 weeks, so if you get into that and it's really uncomfortable, I usually say if it's a discomfort level of above 5 on this first assignment, you're going to have a very uncomfortable time in this course, because I will tell you this first assignment is distinctly less conceptually complicated than the other ones. Though the setup is so annoying. If you're like, Casey, the setup makes me want to die, I know. Guess what? That never goes away. You will always feel that. Every new job, setup kills all of us. So, trauma bond. But to help you, office hours are officially starting this week. Those have also been posted to the course website. One thing I just wanted to show you is, so this is the office hours page. It's got some descriptions, things like that. It's got some stuff in here because I know navigating our 2 buildings can be a little difficult. But it might look like this. This is just a Google sort of insertion thing. If you click on week, that's probably a more easy to follow visual for you. And there you can see all of our office hours. Some of the office hours in the evening are virtual. So we've got a couple virtual for those of you that's a better solution. Otherwise, they're kind of scattered all over the CS department. So please feel free. The TAs are there to help you with any of the download stuff, et cetera, things like that. You're also welcome to post on the Ed board. We're trying to help folks out in that manner as well. Cool. Yes. Yes. All office hours are sort of first come, first serve. Okay. So the other component of this assignment is your ability to actually go on Gradescope and give us the GitLab, and then we run our tests. Sorry, that is not yet posted. Insert comment about SSH keys and that shenanigan. So right now, this assignment is due on Thursday, but if we can't get that Gradescope thing working, we're not going to punish y'all for that, so we will adjust the turn-in, okay? I promise you. If anything I care about in this class, it's fairness, and I'm never going to penalize y'all for us being delayed on stuff. So keep your ears to the ed board for any coming announcements as to when that might be posted and some more flexibility on turn-in so that you all have the opportunity to engage with it actually on Gradescope. If you haven't yet, gradescope.com is where you want to go and then use this add code to formally add yourself so you have access to it. That is also where we are going to post our exercises, and your first exercise should be releasing hopefully tomorrow. We'll make an announcement about that, and that exercise will release, and then it will cover stuff we do in lecture. And then, like I said, to try and help lecture feel extra relevant, pretty much every day I'm going to pick a question from the exercises, and I will go over as close to that question as I can get away with without it being verbatim. So I'll go over a question where maybe I just change the language or the numbers just a little bit so that you can then go and mirror that on your written exercise. So right now the plan is to have the programming assignments in and out on Thursdays, the exercises in and out on Tuesdays. That is subject to change, but I will post it on the ed board. And then one thing also, so the exercises of which I'm pretty sure there are 7, maybe 8. I should count them better. But just so you know, they are partially auto-graded and partially hand-graded by TAs. The stuff that's auto-graded is like multiple choice questions or enter in this number, anything we can tell a computer to do. But every exercise is going to include one sort of long-form answer, and it will mirror the style of questions that are going to be on our written assessments in this class. Reminder, our assessments in this class are in person on February 2nd and March 1st. So we will have one question similar-ish to those on each exercise. The TAs actually have to go and grade them. Unlike the programming assignments, you will not see your grade on the exercise until after the TAs grade it and turn it back to you. And then we don't actually release solutions for the exercises because, you know, we got to like reuse them and stuff. So lessons learned from past quarters, a lot of students ask, can we remake an exercise? Is there any way to improve our score? And so what the TAs have very thoughtfully advocated for on your behalf is that we've decided if you attend all sections, section 2 through section 8, then we will drop your lowest exercise grade. And that's because the section content is directly targeted to help you do well on the exercises. So if you go to section, we're willing to drop one exercise. This is me telling you this so that please go to section on Thursday, starting this Thursday through, I think, section 8. Those are the ones that we know are so directly tied to exercises. If you attend all of those, you will be able to drop an exercise. We are working on how to allow you to do this remotely, but we will talk about the details of that. For right now, please just plan to attend your sections in person as much as possible if this sort of drop your lowest score is something you're interested in. Okay, that was a lot of announcements. Questions about anything administrative? Cool. Oh, yes, please, in the back. If you are unwell or unable to attend physically in person, we will find some way to give you a, like, do this instead and we'll count it. But we haven't figured out exactly what that process is yet. So we'll find something and we'll let you know what that thing is in time. If that happens every week, we might get suspicious, though. Cool. Okay. Oh, yes, please. So exercises you can technically resubmit until the deadline, but submitting won't tell you anything. You're not going to get any immediate feedback. So if you like decide to change your answer, you can change your answer as many times as you want up until the deadline. But also just FYI, we always take your latest one. So if you want to go in and change your thing and now it's late, we will take the late one instead of, you know, the on-time one. So we just take your latest exercise submission. Cool. Okay. All right. So at the end of lecture on Friday, we were sort of talking about these trade-offs, and I skipped over a couple slides, and I just wanted to dive into them kind of more quickly here. So trade-offs. That's really the name of the game that we're talking about in terms of this design stuff. So, you know, we kind of reiterated this in the warm-up, but to kind of take it back to the big O notation format, remember that we have what we would call complexity classes, and those are categories of how the runtime relates to the number of items stored in your structure. So, for example, accessing a single index in an array is what we would call constant, or O of 1, because that takes the same time regardless of how big the array is. If you're trying to get the thing at index 2 and there's 200 elements in the array, that takes the same amount of time as if there's 2 million elements in the array. You just pop in, it's constant, it's independent of how big the array is. If I want you to insert something at index 0, well, that means you're going to have to shift everything else to the right. And if there's 200 things to shift, that's going to be shorter than if there's 2 million things to shift, meaning the relationship in the time to do that code is directly related to how many things are stored in the array. That's what we would call linear. And we compound from there. So let's talk about this then in terms of array list versus linked list. So I just kind of talked through this first one. The time needed to access the nth element of the array. That means some sort of theoretical 0 to, last possible element inclusive. For the array list, what is the big O of time to access any given element based on its index? Can anyone raise their hand? Yes, way in the back, shout out. O of 1, you're absolutely right. That's constant time. Again, doesn't matter how big the array is, we jump straight into the index. Okay, now in the linked list implementation of a list, we no longer have indices. So for us to find, say, the item at index 100, we have to start at the beginning and we have to count to 100 until we get to the node we're looking for. So can anyone raise their hand and tell me what they think that complexity class would be? Yeah, here in the front. O of n, absolutely. That's linear time because it's dependent on how many nodes we have to jump over. Okay. Time needed to insert at the nth element for the array list. Yes, here in the front. That would also be O of n. It's also linear. Now, we might be able to jump into it, but we have to do that shifting. And that shifting, I always like to think, what is sort of the most expensive example of n? In this case, the most expensive example of n would be O, or 0, because inserting at 0 means I have to move absolutely everything else. So that's that linear time there. Okay. What about time needed to insert at nth element in linked list? This one could be a little trickier. Yes, over here. Absolutely. O of n, because we are assuming it could be anywhere we want to insert. Now, if we knew it was going to be inserting at 0, that's a constant time because we're just going to pop it right in at front. But like our friend just correctly identified, what if I told you to insert at index 100? You would have to start at front and count to 100, and then you would insert. So that time to find where you're inserting, that's where the linear is coming from. Wow, y'all are, yes? What an incredible question. Are we talking about the worst case or is there an average? In fact, my friend, we are going to spend most of the rest of the week answering that exact question because the answer is kind of both. And I will specify whether I mean worst case or in practice case or things like that. But actually, it'll take me a whole day in lecture to get really specific. But if it helps for you to start thinking about it right now, I will tell you that in general, when you talk to an engineer, we are pessimists when it comes to runtime. So when somebody asks you for the runtime, they're asking what they think the slowest possible runtime might be given the scenario. So if that means worst case in your brain, start thinking from that directionality. And I'll tell you how to define that in future lectures. But great question. Okay, let's talk about space. This is something that we don't quite talk about as much in academia, but I can tell you we care a lot about in industry. So let's talk about the space. So amount of space used across all elements, or across the collection of elements. So in an array list, because of the contiguous memory, we are going to shove everything together in RAM. But remember, because arrays are static sized, I always need to create a new array that's going to be bigger than the amount of data I currently have stored. Meaning that as long as I'm working with that array list, there's always some amount of sort of extra space at the back of the array so I can add things in. And theoretically, that extra space shrinks and shrinks and shrinks until I run out of space, and then I got to create a new array with double the space and all that. So with the array implementation, I'm always going to have some sort of like extra wasted space because capacity always needs to be bigger than size, i.e. how many things I'm actually storing in the array right now. Then in terms of linked list, what's nice about this one is we're going to call that compact because I tell the computer partition a new node every time I actually have a new piece of information. So I don't need to sort of like keep extra capacity. So overall, maybe linked list is more compact size-wise because I don't have that extra sort of like, surplus space hanging out at the end. Then let's double click. What about the space used per element? What do we think which one do we think uses less space per individual element, array list or linked list? Yeah, here in the front.
Probably the array list because there is a predefined amount of space and then each individual element would only take that much space. Whereas a linked list, each individual element would need the data and the reference to the next one. So
Absolutely correct. And so in this case, maybe array list, we call that minimal because the amount of space per element is just one index of the array, which is optimized to just however much space we need for the reference to the object or the space for that individual int, versus the linked list where we have an object that stores the piece of data and the reference to the next node. So those are going to be a little bit bigger, depending on how you define your node. So these are just, again, ways to start to think about how we trade off in terms of design. Questions on this? Yes?
I don't think that's necessarily true all the time because if you have an array list that's holding, for example, like addresses, 64-bit,
Sure.
and then you have a linked list that's holding a character, something. Is it ever possible that your array list would take more space per element than your linked list?
So I'm not sure if this is what you meant, but in that context, I am, and I maybe should have made this clear, that this is where they're storing the same, like we're looking to store the same thing. So in that case, if we're storing an address, it's to some object, maybe it's the song object, the thing the linked list would store would be an address, and the actual thing stored at the element of the array would also be the address. But in the linked list, we would have a second address to get to the next. So in that like apples to apples comparison, the linked list would be a little bigger. Any other questions? Sorry?
Is it 2 times bigger to have 2 fields?
Ooh, is it twice as big? Well, it depends. So the next field is an address in memory, and depending on what your computer is, 64-bit probably. So that's maybe that amount of size to get to an address in memory. If it's objects you're storing, it probably is kind of twice because you've got the reference to the element and then the reference to the next node, and those are 2 addresses versus the array where it's just 1 address. But if it's like an array list and a linked list of ints, maybe the address in memory, certainly larger than an int, so it depends on what you're actually storing in there. And remember, it also depends on the type of linked list. What if we did a doubly linked list? Or what if we did, a reference to the front and back? Those are also things we might store. So the linked list node might be even larger than twice as big, depending. Depends on what's stored in there. Yeah? Sure. Sure, no worries. Yeah. So you're right. I'm doing this in this sort of language agnostic way right now. And so what we refer to Java as is that's a memory managed language, meaning you aren't interacting with the, sort of operating system directly. C has a little bit more direct control. And so there are probably ways in languages like C where you are being very intentional about how you partition extra array space, things like that. But we're going to sort of like lift up one level for those of you that you don't have to worry about this conversation. But we're always going to talk about what if you don't have any control over the memory. But you're right, there are clever ways maybe to work around it depending on what language you're working in. Cool. These are great questions. Okay, I said I was going to try my best to get you out of here at least 10 minutes early. You can look at these things. We talked about that. I'm going to kind of move through this. There we go. I'm going to talk about some other ADTs. Now, these ADTs here, I'm sorry I'm going to blast through them. I do kind of assume that you are familiar with stacks and queues, and we are going to spend most of this course talking about dictionaries. So I am going to slip through these slides rather quickly. You'll have the slides available to you. But the points of all of these are just what we sort of talked about in the array list versus the linked list, for you to start to think about these are different types of functionality. How might you implement them using an array? How might you implement them using a series of nodes? So a reminder, a stack is the ADT where it is first in, last out. Like I sort of mentioned, I think of it as a stack of lunch trays. You often see it sort of articulated where it's sort of this vertical thing where you put something down into the stack, it kind of falls down to the bottom of the well. The next thing that gets added kind of falls on top of it. And so if you want to get something out, it's the most recent thing you put in that gets popped off the stack. So how do we implement those? If we implement it with an array, well, we maybe push the first item into index 0, then we push the next item into index 1, which means the top of the array is at the back, or the top of the stack is at the back of the array, and the bottom of the stack is at the front of the array. So if I pop, I'm going to pop off of 1, and then if I push, I go back into that space of 1, and see how that very first thing, that 3 that I put in there is kind of untouched? Because again, it's first in, last out. So let's kind of talk about this big O notation. If I pop, that's going to be a constant time because I know which index of the array is going to represent the top of the stack as long as I maintain a size variable. The top of the stack will always be at index size. Right now there's 2 items in the stack. That means the top is at 2 minus 1 because we use zero-based indexing. So I can just pop in and grab that thing. Peak. Peak means look into the stack but don't remove it. So its runtime is almost always exactly the same as pop. Size, we're going to maintain a separate size field that updates whenever you call methods. So that's just going to be return a field, constant time. Never implement a size method where you actively go in and count everything up every time. Instead, create a field that maintains the size that you just returned. Is empty, same thing. We just check if size is equal to 0. And push, so push, in the examples I showed you, constant. We just dumped it into an empty space in the array. But again, we hit that issue with arrays. If we're out of space, you got to make a new one. You got to copy everything over. And anytime you do that, you hit a linear runtime. Quick questions on this? Okay, let's talk about a stack with nodes. So I push 3, it's at the front. I push 4, we add a new node, and we change the pointers. So front is now pointing at 4, and 4 is pointing at 3. Pop, we remove whatever the front is by skipping front. So we get constant run times all the way down because actually linked lists tend to be a good partner for stacks. Because if you think about what a stack is, it's like you're only interacting with the top. And it kind of doesn't matter how many things get pushed further down. So if you only care about interacting with whatever is connected to front, that keeps us a nice sort of constant time runtime. Really convenient. Okay. Fun fact, stacks were, I believe, invented for the undo feature. And that's what's happening in the undo feature, right? Because if you ever notice, every time you hit undo, it undoes the most recent thing you did, and then you kind of keep hitting undo until you get to the very start of your interactions. Again, it's reverse that order. So there you go. Also common, matching tags and curly braces. Every time you hit an open curly brace, you push into the stack. Every time you see an open curly brace, you pop from the stack. And if those things match, then hopefully your squiggly red lines go away. That means good stuff. You can read some of this stuff. Okay, let's talk about queues. Queues, like I mentioned, that's sort of like waiting in line, politely waiting in line, theoretically. You're the first person to arrive at the cafeteria. You're hopefully the first person that they then ask to take an order. So if we did it with an array, again, we'll sort of treat index 0 as the front of the queue, and we'll treat everything after it as the back. So every time we add to the back, so on and so forth. And then when we remove from the front. What this means, if you can see at the bottom of this slide, is now we have two supplemental fields, something to tell us where the index of the front of the queue is and where the index of the back of the queue is. In the stack, we could just assume the bottom was always 0 and size was our top. In queue, we need to maintain two separate things because it depends on how people are getting pulled from the front and added to the back. So we're actually interacting with two different sides of this object instead of just one in the stack scenario. So we end up with constant runtime, again, because we're just jumping into spaces of an array, unless we have to do that resize thing. Oh, but Casey, what happens if we remove everything? We have all this extra space at the beginning. Here, you can see that you can do this wraparound situation as long as you maintain those two separate variables, so that actually the array implementation of the queue can kind of look a little funny, where maybe the start of the queue, the front of the line is at index, say, 3, and then it kind of wraps around, so you use up all the array space. But we might also have to copy everything over, and so you need to copy everything over once the front and the back have swapped directionalities like that, run out of capacity. Cool. Okay, we're doing it. Great. Okay, implementing a queue with nodes. Well, wouldn't it be convenient if we just maintained a front and back pointer? That's how I have ways to interact with this object at both the front and the back. I'll just, again, make two separate fields, one for how I add things, remove things from the front, one for how I add things to the back. And that gives us constant runtime all the way down for the queues. I think that's... Yes. Oh yeah, these are real ones, tasks, scheduling, things like that. We are going to talk about priority queues later in this course, which also are very common. Scheduling printer jobs, scheduling CPU tasks, things like that. Does anyone have any questions about the queue implementation methods? Yes? So what's interesting is, in this class, I'm talking all in the theory level. I'm talking in the big O theory space. But for context, big O only takes number of instructions and code to things stored inside of it. It doesn't include how much faster it is to iterate over contiguous memory. It doesn't take excess memory into account, things like that. So you'll find that when you actually use a stopwatch to time things, even though the big O might look better, at smaller values, array typically is faster and will be the preferred way. You'll probably find out on the internet, most folks implement all of these with arrays as the underlying structure, even though the big O analysis says linked lists are better. And that all depends on scale. So because you can imagine, if we have so much data that we have this data scattered across multiple machines, that contiguous thing doesn't give us the boost anymore. They might be, we're talking about distributed systems, linked lists, things like that. But you will find on average, most people even lean towards array because of that sort of contiguous memory bump. But if you're in an interview and somebody asks you this stuff, you're going to be the smart person. You're going to be like, well, the big O analysis of linked list is all constants, which is really nice. So I'm going to implement that. And the interviewer will be like, yay, that's the best. We're just here to talk about theory. These interviews are not actually about implementation in the real world. There you go. You're welcome. Okay. It is 4:09. The last thing on here is dictionaries. Like I said, dictionaries, remember that is where you have two pieces of information. The lookup, which is called the key, and the thing you're looking up, which is the value. I like to think of it literally as a dictionary. The lookup is the word, the value is the definition. But since it is 4:09, I am going to leave these slides. You can read them on your own. Come back on Wednesday, and we are going to start to get into the real fun math stuff. Have fun watching the game. Go Dogs. Put out all of the good vibes. I believe in us. We already beat Texas. Come on.